Good day, I'm Norman Wahlberger, and today we're going to carry on with the Math Foundations series, moving into a very important topic where we finally address the core problem with modern pure mathematics, which is its over-reliance on set theory as a foundational framework. Now, I'm jumping ahead a little bit in the Math Foundations series. So there's a segment of videos that I'm planning on doing on abstract algebra, and I'm going to be doing that at some point. But I want to jump ahead now to embrace this very important challenge of looking squarely on at the difficulties that we're facing and actually examining the details of what we're currently doing at the foundational level. So in this series so far, we've put together, I think, a fair case that it is possible to do a lot of mathematics correctly and logically from a solid foundation. We don't have to ignore the foundational issues and pretend that everything is good. We can actually build things up slowly and steadily, and it's really instructive to do that. It empowers us. It doesn't weaken us, it empowers us. So in this spirit, I want to now examine actually at what we are currently doing officially, and I want to dismantle it. Okay, so there's really an elephant in the room in pure mathematics. We really have painted ourselves into a corner. The reality is that modern set theory is just a logically inadequate foundation for mathematics. So to present this case, we're going to look at the history, we're going to look at some of the people involved, the controversies that have dogged the subject, even from its early years. We're going to look at the sociology about it too, because that's an important aspect. How is it that a whole generation, or actually several generations of mathematicians have managed to just not look in that direction? It's very interesting, but ultimately it's really the logical structure that dominates the discussion, right? Finally, when the smoke clears, it is all about logical correctness and clarity of definitions. The number of people that you get to voice an opinion in this direction or in that direction is ultimately secondary to the logical integrity of the arguments that are presented. All right, so let's put set theory on trial. I will be the public prosecutor and you can be the jury. And I want to present the case, and at the end of this case, which will take quite a while to develop and lay out for you, I hope to move our current view to a new and more solid view. Currently, we believe something like this, that in the realm of pure mathematics, there is the foundation. The foundation is set theory. Everything is built on set theory. Supposedly. Arithmetic, geometry, combinatorics, algebra, analysis, topology, differential geometry, algebraic geometry, all these subjects are built up with set theory as the base. No, people. It's not the way one should think about mathematics. And we want to move to a future view, something like this, where mathematics is built up with arithmetic as the foundation. Very simple kind of arithmetic. Arithmetic with natural numbers. And from that basis, we build up higher arithmetic, geometry, combinatorics, algebra, analysis, and so on. And set theory, which was over here, the foundational part of mathematics, is moved to its proper place, which is as a branch of combinatorics. There it is there. It's not discarded, it's a very important and nice subject, but it's just part of combinatorics. And it shares space with multi-set theory, with lists, with other kinds of data structures. What we're also going to do, which is perhaps a little bit novel, is we want to correspond, make contact with what the computer scientists are doing. This is going to be increasingly important from a foundational point of view for modern mathematics. We want to be in sync with what our machines, what our computers doing, because the computers are going to be playing an ever-increasing role in modern mathematics. I'll have to talk more at length about that. It's a very important development. So we want to sync with computational issues. And this is, I think, the framework that we're going to have. Something in this direction. We're going to see that it's a much more solid and natural and historically viable way of thinking about what mathematics actually is. So in today's video, I want to give you an overview of the situation that we find ourselves in and explain to you some of the reasons for the difficulties that we find ourselves in. And a lot of it has to do with the nature of the continuum, the line, trying to model that in mathematics. I talk about that as a fundamental problem in my famous math problem series, number 19. But let me explain it here. So there's a fundamental difference between the discrete and the continuum in mathematics. And the discrete is modeled by the natural numbers to a first approximation. 1, 2, 3, 4, 5, and so on are counting numbers. And that's very concrete and workable, even though we must acknowledge that as we go in that direction, as the numbers do become big, then arithmetical problems arise. So this is not an ironclad framework because of the difficulties involved in big arithmetic. But at least up to a certain point, we are very comfortable with it. However, the story with the continuum is very different. With the continuum, we also face the same kind of problem that we do with the discrete natural numbers, namely what happens actually when we keep on going in that direction. Can we keep on going infinitely? If not, is there some bound? Or what exactly happens? So that's a subtle issue, the same kind of issue that we face there. But in addition, in the continuum, we face this local problem that's right in our face, that's not off the page, it's right in front of us, which is how do we model what's actually going on if we look closer and closer at the nature of this line? How do we do that? What's the mathematical way of magnifying and subdividing and looking more clearly and carefully at smaller and smaller subdivisions? So this is hugely problematic. And one of the issues here is that from a certain point of view, it might be tempting to introduce things called irrational numbers. Okay, so this happens, let's say, from the ancient Greek times when you look at a square of side 1 and you look at its diagonal there. So the Greeks thought of this diagonal, that's a segment. Okay, it doesn't necessarily have a length. But if we take that segment and we move it so that it's not facing slanting up in that direction, but we move it so that it's on our axis, then we have a segment here which is incommensurable with the segment of the side of the square that we started with. This is the fundamental irrationality that the Greeks discovered. And while they expressed it in terms of incommensurability of segments, it wasn't for them arithmetical at all. For us, it manifests itself as the existence, supposedly, of irrational numbers. So we believe that there's some kind of irrational numbers in there somewhere that sort of correspond to the length of such a diagonal. And we want to believe in such lengths and we want to believe in such irrational numbers. And so we are faced with this conundrum of how do we set up an arithmetic which incorporates not just rational numbers, but also these irrational numbers. Okay, this is hugely problematic. It's hugely problematic, and it's really the source of almost all of the difficulties ultimately with modern calculus and modern analysis, and ultimately with modern set theory too. So if we condense 2,000 years of mathematical history in just a page or two, we can say that difficulties with infinite quantities and infinitesimal quantities were already apparent to the ancient Greeks, and they tried to position themselves, especially Euclid, to try to minimize these difficulties and to try to deal with them squarely. But in the 17th and 18th century, in the European development of the calculus, there was a huge expansion of mathematics, most of it motivated in the direction of applied mathematics, of solving real problems. And it was very powerful. And after that, in the 19th century, we saw a slow emergence of what is today usually called pure mathematics. So it's a relatively recent development where people were going back to the ancient Greeks, which they did have a very pure point of view, but it was sort of lost for a few thousand years. And then in the 19th century, people started saying, okay, what exactly are we doing when we're doing this calculus? This calculus is great. We've got all these cool tools. We can solve all these problems. But what actually theoretically is the foundation for what we're doing there? How do we deal with the challenges that calculus throws up to us. And so there were some efforts then to try to put analysis on a firm footing. And eventually people realized that it really came down to this continuum problem. That's really ultimately the heart of things, is how do we actually model the number system upon which we're building our calculus? Okay? And eventually people said, okay, we'll take these Stebbins decimals and we'll sort of soup that up into a theory of real numbers. Okay? And it's justifying and laying out the foundation for this real number story, which is really where the difficulties lie. It's really where the difficulties lie. And it's very important for analysts to be able to do this because they feel it's necessary to justify what they do in the calculus. So it's quite interesting that this realization that we really have to address the arithmetical nature of our underlying number system, that's really the foundational issue. This is actually a relatively late development. It's really only in the last half of the 19th century that people started getting serious about this challenge. And around the 1870s, Dedekind and Cantor, and then Hilbert, gave constructions, or I would rather say descriptions, of so-called real numbers. They tried to create some framework for the arithmetic of real numbers. And actually later they said, well, if we're going to work on real numbers, maybe we should get rational numbers squared away. So they worked on rational numbers, and then eventually they said, well, maybe we should actually ponder what integer arithmetic is really like. So there was kind of a strange time frame for these various things. Now, it turned out that the constructions, in quotes, of Dedekind and Cantor for irrational numbers, for real numbers, really ended up strongly utilizing Cantor's new theory of infinite sets. So around the same time, Cantor had developed a new theory of infinite sets, which caused a lot of controversy. Many mathematicians, many prominent mathematicians opposed this new theory. Cantor felt himself isolated and under attack, and he was under attack. And it was a difficult time for him. And ultimately, though, his point of view triumphed because of largely the support of David Hilbert. But in any case, there still was a lot of controversy. So around the turn of the century, 1900, there was huge controversy in this direction, as to whether Cantor's theory of infinite sets really did work or not, whether it was an adequate foundation for this sort of real number story, and what the relationship between all of this and the foundations of mathematics was. There was a lot of controversy. And then, unfortunately for this new theory, disaster struck in the form of major contradictions. So it was discovered that there were major contradictions in this newfangled set theory that Cantor had developed, and that was propounded by Hilbert and by Dedekind and others. So this was a very embarrassing, difficult time, and analysts suddenly found themselves without a foundation, because the theory of real numbers that had just been developed previously depended on infinite sets, and now infinite sets were found to be logically questionable. So where are we then? What's the framework for analysis? It was a very difficult time. And unfortunately, a combination of factors, including Hilbert's orientation with formalism, the increasing role of mathematical logic into mathematics, together these things somehow created a situation where axiomatic approaches to set theory were allowed to rise up. And these are encoded these days in what are called the Zermelo-Fraenkel choice axioms. And what we ended up having was a framework which was not really based on precise definitions and clear theorems and such, but it was an axiomatic framework. So it was as if we had abandoned the effort to try to set up this foundational issue very carefully and clearly, and said, let's just assume that it works. That's really what happened. It was a situation, let's assume that the kinds of things that we want to be true actually are true. And we're going to dress this up as an axiomatic framework. And more or less what happened was that the job of framing this all in such a fashion was outsourced to logicians, which was really philosophy. It's really a branch of philosophy that overlaps with mathematics. It's not too much of an exaggeration to say that mathematicians outsourced the foundations of their subject to the philosophers. The philosophers, of course, were chuffed at this. This is great. The mathematicians require their services. They're going to come in there and they're going to build up a framework. And ever since then, mathematicians have, in their minds, sort of put this on a pedestal and said, yes, we now have foundations up there, but we're not going to look at them too closely because it's really kind of philosophy. It's outside our realm of expertise. It's different from the rest of the mathematics that we're doing. So we have this kind of divide. There's a polite agreement not to examine carefully what this logical foundation of set theory is. And it's a very unfortunate situation. And it's, in my view, very parallel to what happened some decades ago with the IBM and Microsoft. So IBM was very excited, had these personal computers, these fabulous little devices that had the computing power of huge rooms previously. And they needed all kinds of components, from various people. And they also needed someone to make an operating system, so underlying software for their computers. And sadly for them, unfortunately, they didn't actually do this themselves. Okay, so it was Microsoft that ended up developing their operating system for them. And it was really a fundamental mistake, right, to think that the software is somehow unimportant or relatively unimportant and that we are able to outsource that. These days, we probably all agree that it's the software which is more important. So in my view, it's very similar to what's happened in mathematics, that pure mathematicians have outsourced the job of creating proper foundations for the subject, so much to the extent that students are discouraged from actively investigating this situation. It's like, don't go there are these foundations, you just believe what you're told, play along with the game, and we're going to concentrate on doing sophisticated, important mathematics. Foundations is relatively unimportant. Well, my view is exactly the opposite. Okay, it's exactly the opposite. I think that ever sophisticated, more and more complicated mathematics is much less important than getting the foundations correct. You get the foundations correct, then things chunk together in a beautiful way. And mathematics becomes a vibrant, a living thing, instead of this thing where we're all trying to do crazy things. So that's what I want to move us towards, but we're going to have to examine this whole story. This is, of course, a major simplification, but we're going to have to examine it carefully, and we're going to be looking at it in some detail. In our next video, I want to go back to the roots of logic and examine how the story of logic has risen from early days and how it impacts onto this foundational development. I hope you'll join me for that. I'm Norman Weilberger. Thanks for listening.